Okay, so the notes are even more important.
That's like or you're ready for that. Well, I figured you would like the answer. I'm gonna try that.
This is the best class, but it's not recorded. I enjoy it. But, anyway, so since I was talking about what makes life for humans easier, I also have this other argument, counter argument to my own counter argument that people do write C programs despite there being much better. I mean, I'm currently Python. Despite there being, in fact, I think the old days I used to see this T-shirt saying, 30 years of research into programming languages and C++ is the result, big question mark. So the point is sometimes you don't know. I mean, it's like I'm kind of deciding what kind of advice is easier to give. And I came up with this nice idea about giving advice which can be interspersed, etc. But it is also, I mean, there is no actual study, carefully done study showing that humans will be more likely to give, HTMs that are partially ordered than ones which are like basically contiguity ordered. Basically, humans will do anything if you pay them. Essentially, they'll do programming in C, right? If you pay them enough, right? So that's one thing that I do want to put out there. And the other interesting point is that in general, much of this from the planning perspective should be seen in terms of domain independent versus domain specific versus domain customized. Okay, so domain specific planner would just write the planner only works for that domain and nothing else. And so in fact, the domain specific planner it only requires the goal. That's it. Okay, domain independent planner requires the domain model and the initial state and the goal state. Domain customized planner essentially is requiring initial state, goal state, domain model plus extra stuff like the advice. Okay, and this advice essentially is making that be more specific to a domain, more specific to a user's preferences. If you follow the task direction schemas, then they can be more specific to the user. So in some sense, this has been called, in planning, this whole thing has been called knowledge-based planning. And which is kind of a strange thing to say, as I mentioned last time, it's all knowledge, except they mean advice-based planning. Domain dynamics is different from advice. Okay, that's the other thing. And there are different kinds of customizations people have tried. I mean, I already told you multiple types of abstractions, but if you think in terms of just domain customization, people have tried not only the HTMs, but providing control knowledge for search, at any, in the A* search at any given point where you go to pick between different children, then there's a control rule saying under these conditions, pick this kind of a child. It's a very fine-grained, advice. You can actually learn them. There's a lot of work on explanation-based learning, ETL, control rule learning. That kind of makes it more specific. You can learn that. And then there are people who actually said we can just change the action specification itself by putting pseudo preconditions and pseudo effects on top of it. Okay. And so, for example, when I was showing the partial program earlier for that soccer-like game, I can have an extra precondition saying you are in possession of the ball. It's not a state condition, it is some abstract condition that you made up. And then you have to then actually give a piece of the domain model that actually gives that condition. Under what conditions that model, that condition will be true. You see what I'm saying? So that's another way of giving advice. And this is actually, if you think about this, it's it's not surprising. Remember the way we talk about compiling partial satisfaction planning into MDPs, where I increase the state space with an extra thing called done, and I change all the actions. Okay, this is a way to play around with the model such that it will generate, will basically work. So when you did that, for example, that MDP is only good for partial satisfaction plan. It's not good for normal planning. Right? I mean, in the sense that it was specified, it's kind of the state space has been exploded so that you can also do partial planning, partial satisfaction planning. Okay. And then, of course, there have been a bunches of learning techniques such as search control low learning, plan reuse. And in fact, there have also been learning techniques for learning domain models from plan traces. Okay, so there are different kinds of learning advice and learning the domain dynamics. And as I said, next class we'll talk about two different, very different approaches for learning dynamics. One on a PDL style and one more pixel style. Okay. So anyway, this is basically domain independent planners tend to miss the regularities in the domain. Domain specific planners have built and scratch from every domain. And any expertise solution is try adding domain specific knowledge to the domain independent planners. This is all assuming that the humans are in the loop and giving these kinds of advice. Okay. You can always say, I will learn, but then when you are learning, then unless the human is part of the loop, then what you're learning may be just to improve your efficiency. Yeah, so anyway, that was that. And I mentioned a bunch of things in the beginning itself, the domain knowledge. Ultimately, the question about the advice is the advice more than domain knowledge advice? Is the advice prescriptive or suggestive? That matters. If it's prescriptive, that means you must follow it. That means actually can increase the cost of the problem, because you not only have to solve the problem, you also have to be consistent with that advice. So in the worst case, it can worsen. Okay. In general, what you're actually saying is that I'm trying to help you by constraining you. That is true. Sometimes by constraining you, I can help you. But sometimes I might myself miss the interaction between my advice and the way your reasoning goes, that actually your life is harder because of my advice. Okay. And then we talked already about HTN, STN. We already by now hopefully know the difference between HTN versus trips planning. And one last thing on the HTN side is, in addition to TSTN, if both HTNs and TSTNs, they are still declarative advice. They just give it as a constraint. They don't go into the innards of the planner and say, now turn left, now turn right. In particular, if a particular non-primitive task can be reduced by 15 different task reduction schemas, you don't tell which one to use, because that becomes a control knowledge. Basically you're just hand holding and walking the planner through the search space. But on the other hand, you might say, if I'm doing all this, why not just hand hold and write the planner? Okay, and so that actually is this idea called SHOP, which is, I don't know what it stands for, like people have something partial program. Basically, you write a high-level program for the planner, and it just follows it, essentially. And if you know enough about the domain to write this, you can never be beaten by any first principles planner, because you know so much about the domain, you know exactly when to do what turns, etc. Not just advice, but you're actually controlling the underlying strips planner. You see what I'm saying? And the question, of course, then is, if the SHOP program, which is SHOP itself is a planner, and if the planner is wrong, then whose mistake is it? There is no difference in the SHOP scenario having in terms of a strips planner, which is trying to be consistent with the task reduction schemas. That is true for whether you have HTNs or ESPNs. But once you come to SHOP, this is the only way you get to a strips planner, if at all. What I'm saying? And this actually, it will sort of kind of made fun of in planning community. But lots of people who just want a good planner for their particular domain, and they only care about their domain and they don't care about anybody else's domain, and they have the time, they just write the shop program and be done with it. So if you think about actually planners that have been used using the PDL style operations, etc., shop has been used a lot more than anybody else. You can't take it as it, you can't stop people from using what they don't want. Okay. So that's shop. And so this is plus the domain specific and domain independent divide. And again, the question, of course, is how you're essentially writing a planner in a high level language. The reason, and then there are also, by the way, before I go forward, that there are other kinds of non-HTML declarative guidance too. There's a guy called Fahim Bacchus who actually, yeah. So the declarative guidance, basically, you could actually give additional constraints that must be true of any trajectories, either because of the physical limitations or because that's how you want. And in fact, a guy called Fahim Bacchus, who unfortunately passed away 2 weeks back, wrote this planner called TL Planner. And what TL Planner does is it gives advice as CTL formulas over state trajectories. Because all plans are state trajectories. And you could basically say that good plans will have the following kind of regularities. If in fact these conditions becomes true in this state, then eventually this other condition should become true. You know what I'm saying? And I don't seem to have that slide here, unfortunately, but he actually gives, I'll show you that on the Piazza. He has given a set of CTL rules for writing, for doing good block sort plans, irrespective of what the goal is. And if you essentially, and he gives a TL planner, essentially is a thing which can consider this CTL rules as well as the strips actions in deciding which action to do in the forward state space planning. So it's basically controlling. It's like a heuristic. The TL plan rules become the heuristic. And it just is blazingly fast. Except, I wish, since I brought this up, I wish I had that particular slide. I don't know where it is. But the CTL formulas are pretty darn hard for anybody other than Fahim Bacchus to have it. So much so that I had one more slide, which also is like buried somewhere, where I used to argue about this whole knowledge-based planning at one point of time and say, you can get Sharp and also download an instance of Dana Now, who wrote Sharp, so that he can write the Sharp program for you. And similarly, you can get TL Plan and download an instance of Fahim Bacchus because he thinks in CTL formulas. Do you understand what I'm saying? If you're not learning them, if you're learning it, that sort of removes all of this stuff. If you're not learning them, the question is, how hard is it to provide this kind of advice? And that depends very much on who feels comfortable in writing the advice in that. Because then you're now talking about writing programs essentially, right? I mean, and the programs require programmers. Okay. Anyway, so that's on one more thing that was done in the thing. So then I get back to what I was talking about last in the very beginning of the class, which is what if you have HTN schemas, but some of the methods for reducing them are missing. That's the easiest way to get from HTN planning into hierarchical reinforcement. As I mentioned quite a bit, essentially you kind of say those details the planner figures out. Except, as I said, it's much the underlying agent figures out. The underlying agent is doing the search If it is an RL agent and it's actually you want to act like it is experiencing the world, then it has to do state space search. Mostly. Because there is this version of policy search, policy gradient, which is an interesting complication. In fact, the true HTM kind of advice can be given to RL agents if they can do policy gradient search in expanding, in finding the policy. But mostly you normally just do, normal vanilla RLs will just be doing this sort of state space search, either by calling the simulator or by experiencing them. And a vanilla strips planner will just do whatever search, the planning search, basically, right? And so all of those are ways in which you'll say, here is the abstraction. So I'm setting up the constraints, you then solve this sub-problem yourself. And once you solved it, you can remember it as the task directory schema for the next time around. But this solving part, essentially, you can call it searching for or learning the policy, sub-policy. And I would think that's the cleanest way to go from all the stuff we discussed about from the planning side into the hierarchical RLs. Okay. Okay. And so, as I mentioned earlier, typically many of these HRL things can be thought of as partial programs or some kind of like task network kind of programs, except they should make sense in state space because the underlying solver is going to be in state space. Right? And so actually, interestingly enough, DL plan would be great. Because TL plan gives CTL formulas. CTL formulas are very easy to evaluate on state trajectories. By the way, here's an interesting thing. The way the TL plan actually works is it has all these CTL formulas corresponding to the advice. And as it is expanding a particular current plan is like a prefix, right? Because it's doing our forward state space plan. As it's expanding a prefix, it checks to see how many of the TL plan formulas are still not violated. And the moment any partial plan violates all the TL plan formulas, you kill that branch. Just parsing by a different name. It's just that here it is sequences and you're checking whether CTL, how many of you have heard of CTL? Temporal logic. Essentially, temporal logic basically allows you to talk about properties of sequences. Right? And it has additional operators such as eventually, next to, before, etc. And so you can use that to say that if this condition is true, before this condition must have been true. If this condition is true, 5 steps later, this condition must have been true. And if you write these kind of advice, then any partial plan that you're expanding, you can check efficiently. That's the important thing. The thing that Fahim did was he found a very efficient ways of incrementally evaluating the correctness, the satisfiability of all the TL plan formulas. Think about it, it's not that different from CSP. Constraint satisfaction planning, you start by taking a partial assignment, keep expanding it, and you stop expanding if the current partial assignment already kills all the constraints. Actually, any constraint in their case. So actually, even in TL plan's case, all you need is the current partial plan. I'm sorry, I actually misspoke. When you have a partial plan, you want to make sure that the partial plan doesn't violate any of the TL plan constraints. Because all those constraints have to be satisfied. If it violates any one of them, then you can stop. So in that way, it's really like CSP, where you stop if a partial specification violates a constraint. Because once a constraint is violated, you can't make it back. And the same thing with TL plan. It turns out that you have to make sure that for every constraint, you have to keep track of whether the partial sequence still has a way of keeping this constraint alive. Right? And if I had a constraint saying, whenever this condition is true, 5 steps within 5 steps, this other constraint should be satisfied. Okay. Now you made this condition true. First step, this condition is not satisfied. The constraint is still valid. Maybe the second step. Second step also it did. Then third step, fourth step, fifth step. At that point, you say, hey, the constraint is violated now. Because 5 steps are over, the condition hasn't appeared, so this plan is dead. Do you get what I'm saying? So that's what TL plan does, and it basically stops expanding certain partial plans if they no longer can satisfy one of the TL plan constraints. And the reason I'm bringing this whole thing is that CTL formulas can actually be written as the kind of partial program that HRL systems tend to assume, because they can be directly evaluated over state sequences. Okay. But in general, one example, as I said, this is actually from Stuart Russell's 4th edition. That's the one reading that I didn't give, but that's what I wound up reading before coming to the class. And so here, as I said, he made up this additional terminology. Well, each terminal is, if it's not yet terminal state, then if you have the ball in the position, then do only these 3 actions. Otherwise, do these only 3 other 3 actions. Notice that this partial program would make it HRL, whereas this is also a partial program. This just says do any action that is doable. So that's why HTM can be trivially made equal to strips. You understand what I'm saying? HTM can be trivially made equal to strips, and similarly, here the partial program, if it's an empty partial program, then it will become normal R. If it has more structure, then it is actually constraining the choice of the RL agent underlying RL. Because of which it's no longer MDP, it is semi-MDP, because you can view the decision as to what actions I can do from the current state, not just as a function of the current state, but the function of the state and the partial program. In particular, the partial program might actually be telling you, you are at this particular point in the program counter. If you are in this program point and it is in this state, whether or not you get to do the action. Think about within 5 steps after this condition becomes true, this other condition should become true. So there is an actual counter that is counting the number of steps that have elapsed after the condition became true. It will say, fine, you can do any act, you can expand this, do any actions whatsoever until the counter reaches 5, at which point, hey, you're done. You see what I'm saying? So if you ask yourself, HRL is semi-MDP, what about MDPs or graph search? MDPs are graph search, generalized graph search. Okay. Hierarchical reinforcement learning basically corresponds to many cases, including options, correspond to semi-Markovian processes. So the question is, did strips planning became more than a normal graph search when you considered any of these abstraction ideas? It did. You just didn't make a big deal about it. See what I'm saying? Different communities make big deal about different things. Okay? Because essentially, if you are keeping track of some advice and saying certain actions cannot be done from a certain state, either you can do it one or two ways. In the case of planning, you don't say that you are stopped from acting. You come up with a plan and I'll say whether the plan is correct or not. Right? And so I will come up with a plan that is strict correct, but then it's not possible by the schemas. Then I'll say it's not a plan. What happened? Because it wasn't strict planning anymore. It wasn't like, your action that you do just depends on what state you are in. Your actions are actually being in a very indirect way controlled by these task reduction schemas. You see what I'm saying? If you are in the bus station, you don't get to dance. Because the bus reduction schema says, if you are in the bus station, you buy the ticket, you go into the bus, you keep quiet. You see what I'm saying? Well, I gotta dance. I can dance, I gotta dance, but I can't because of this stupid schema. So it was of course MIM. It's just we don't make it deal about it. Okay. Now then finally, who gives the partial programs though? In most HRL papers, the partial programs are provided by the human programmer or some high-level symbolic module. In fact, one of the strong ways this happens is when you do combined task and motion planning. Where you might do motion planning with some RL kind of an agent and task planning is done by somebody else, like a symbolic planner, who then started with a abstract PDL model. So as far as the motion planner is concerned, it's being given an advice saying thou shalt move only in ways that are consistent with the task plan that I give you. Okay, that is one way. The other way is actually Stuart Russell or you sit down and write these programs. Nobody ever says how hard is it to write these programs. They'll all give good examples for which it's so easy to write. Do you see what I'm saying? And say, look, it's obvious that in this silly soccer game where all that matters is if you have the ball, you keep it. If you don't, you give up. Since I know this, I'll just write it as this very small partial program and look, I can do much better with this. And you can't argue with me that this is cheating. It's so small. This program is so small. Why can't I give it? And I still want to be called doing learning. You know what I'm saying? Okay, unless you learned this also, you can't say you're doing RL per se necessarily. So it's a very interesting, complicated, discipline right now where certain places they don't mind people just giving stuff from outside in HR. But certain other places they want to do the search themselves. Actually, they call it learning, but they're basically doing search if you have simulated. Okay, and the reason I bring this up is not to say that it's wrong, but to say that there's so many connections across the two fields now that you know this point. In fact, I have this paper which actually reinvents main subaction restriction. I kid you not. Which has been written about by my PhD buddy, Chang Yang, in 1905. And there is a student of Dynaprica who more or less reinvented this. That person is not cheating. If you don't read, you are not cheating. If you read, then that's sometimes they say, I don't want to read because that way whatever I say, I just made it myself. Okay, remind me, I'll send you that paper. But that's the kind of thing that basically makes me that there is a lot more that people can learn across. Okay. So the second part about HTN versus HRL partial programs is unlike the general plan space HTNs, partial programs here are in state space terms. I already said this. Most of what I said, I've said multiple times before by foreshadowing. Right? So in a way, they are more like abstracts. The original abstracts, the planner, where remember it would do some preconditions only and level 1 precondition at the first level And then in the level 2, basically you never get out of your lathe. You understand what I'm saying? And I then said, well, if you're thinking of it as a plan space planning, just think of the precondition as ordering and be done with it. Goal ordering and then open condition ordering. Because you're thinking about the state space terms, then you needed to have that contiguity constraint. Okay. So basically the partial programs that HRL tends to use are more like PSTNs, which really should be called CSTNs, contiguity. Okay. Most ideas for HRL have been the state space terms with the assumption that the RL agent will fill the blanks by learning the context, learning within the context of the partial program. Okay, the simplest would be, I did not know that, but the simplest would be in my quaternary path planning. My God, I mean, it feels as if I just had this tremendous need to talk about my MS thesis. But, I got these things, this big gray node has been put as part of the plan. The entry point to the gray node and the exit point to the gray node depends on the other nodes that are on both sides. And I figured that out. You see what I'm saying? So that's basically, I was calling it search because I did not know the RL term, but you can call it RL, and then if you have a simulator, that would be right. But again, the bigger point is it's not, unless the world is non-ergodic, and the world will always be ergodic if you have a simulator. There's really no difference in RL search. Since I'm making everybody unhappy, why not Rich Sutton too? And so, Rich Sutton would be very unhappy to hear this, but there really is no big difference. What is Monte Carlo tree search? It's an RL method, but it's doing search. You can do exploration in the context of search. Thing that makes RL is you're actually doing experience in a non-ergodic world with no guarantees. That would be quite interesting. Okay. And then if you really want to support actual plan space HTMs, then the underlying search needs to be able to search in plan space terms. For RL, that would be policy search and the policy gradient search. Okay. It's actually doable. I don't actually know. In fact, the guy who could have answered that question just stepped out. Lynn might know some. Do you know anybody who does hierarchical RL with policy gradient, the underneath?
The policy sketches work that I had sent, which is by.
So by the way, policy sketch itself is a partial program on the policy. Policy sketches would be connected to HTML.
Sergey Levin, like some of the people
they do find out. So when you do the policy search underlying, then you're you're basically doing something more closer to HTML planning in the analogy across the worlds. You see what I'm saying? Okay. And then we have, and I know that it's kind of hard to understand unless you know what policy gradient search is. Typically, the one sentence description of policy gradient search is you start with a differentiable parameterized policy, and then you need to change it by gradient descent. Except the gradient involves, if I make a little change to this policy, how much would the value change? Expected value change. This is not your nice auto-diff gradient. This actually requires running the agent in the real world or on the simulator and collecting reward with and without change over many, many iterations. This is what is called empirical gradient estimate. If you do that, you know what it will be close to? LPG. Remember long back, a couple of classes back, I talked about LPG, which was this planner that essentially starts with the entire plan and tries to make changes to the plan structure to reduce the number of flaws. And it's doing a hill climbing search. Except the goodness of every change can essentially be, it essentially, because it has a discrete number of changes, it makes all those changes. For each of the changes, it sees how many flaws are still left and takes the change that has the least number of flaws. You're doing gradient descent in continuous space. You're essentially doing, gradient descent is nothing but hill climbing in a continuous space. There you change some parameter of this parameterized policy by epsilon and seeing how much the returned value would be. The value is connected to the number of flaws. The value increases means the flaws have reduced in the plan. One very big thing you want to keep in mind is in the planning literature, is a big difference between a valid plan and an invalid plan. In RL literature, there is no such thing. Every policy is a okay policy, especially if you have, if you don't have dominant states. Every policy is okay policy. It's just, as I mentioned, during multiple classes back, it's just as a really bad value. Okay, and so that's policy gradient search. And of course, you could do systematic search for policy search. I think that basically is harder, especially in the non-tabular representations. So basically, the way you would do HTM style thing in HRL would be something more like policy gradient search. And then the other thing really is we spent so much time in the beginning parts of this class talking about, once I give the advice, are you following my advice? You see what I'm saying? One good thing in RL is you never consider advice to be a constraint, especially the abstraction advice to be a constraint. If it works, it works. Otherwise, I can always just go back to the normal one. And you might say that will reduce the efficiency pretty badly, but on the other hand, given that search in the primitive states is so inefficient to begin with, on average, any reasonable partial program can be shown to improve the efficiency. Am I looking cynical enough? In terms of, it's so much nicer to read a paper and say they know what they're talking about. Okay, but you have to understand everybody has to put the best spin on the papers, including myself. If I'm writing a paper. But as a reader, what you are interested in is what are they not telling me? Of course, they're telling me what they're telling me. That's like the first thing you'll get. But the real thing is what are they not telling me? That's where you actually decide, what happens in terms of improvements. A couple more points and then we'll be done. One is, there is this idea in RL called reward shaping. And essentially reward shaping is, in fact, one great way of reward shaping is take an admissible heuristic for that domain, add it to the rewards everywhere, and actually make it the reward for the states. And that improves the value iteration efficiency very much. So basically reward shaping means, and so remember the heuristic depends on the goal state. You get the point? So reward of a state doesn't depend on where you are going. It's like you are here, hey, no, take this as a heuristic depends on where you are going. So if you change the rewards of the state to an admissible heuristic, it works for that particular goal. And it makes you do much better in finding the policy. You guys get that, right? So a heuristic is a reward shaping. In general, abstraction, and anytime you are not just deciding on the goodness of a policy based on just the cumulative reward that you are getting, RL folks will feel very bad because the optimality points are all in terms of the rewards of the states. What I'm saying? And admissible heuristic would not change the optimality, at least for that goal. But you do realize that any kind of an abstraction is effectively changing the reward structure. Right? Because there are certain things that you are not allowed to do, and in essence, the advice is pushing you in certain directions in the state space. So, not surprisingly, any kind of an abstraction can also potentially be written, compiled down into a reward shaping function. You understand what I'm just saying? So, I give you a partial program. I can say that theoretically, not practically, I may not necessarily know it, but theoretically, there must exist a reward function for this RL agent, such that if you find a policy at the base space using this reward shaped reward, it would have all the properties you care about, both the whatever the value returned in the base level, as well as following the advice. So in those cases, actually things like hierarchical optimality, etc., make sense, because you're saying of all the policies, this would be the policy that has the best, all the policies that are consistent with the advice, this is the best policy that has, the highest value. So reward shaping is really connected to abstraction, as if enough things aren't connected to abstraction and you're feeling sad. Heuristics are connected to abstraction, reward shaping is connected to abstraction. And the last thing, which will get us to next class, is representation learning, which I already mentioned earlier, is connected to abstraction. If you are going from state space signal, state and sensory signals to symbols, that's an abstraction. If you started with some particular signal and you did dimensional reduction, that is an abstraction. Is it a good abstraction? Does anybody else make sense of it? I don't know. So a lot of people in representation learning essentially just take, and we will see this in next class, they will essentially do some sort of dimensional reduction on the state space and then hope for the best. And like I said earlier on, what is the chance that you take a picture of, high-def picture of a Bloxworth scenario, and you did some latent demonstrated, demonstrated reduction and went to latent dimensions. The dimensions would be block A, block B on AB. Very unlikely. It just improves your efficiency, but it's not the kind of abstractions that people think of. Okay, so that's a very useful thing to think of. No reasons to believe that dimensional reduction will correspond to any reasonable abstraction of the kind we talked about. There's so many kinds of abstractions. The one we talked about, the kinds of ones we talked about, none of them would be followed by just upfront just finding some latent dimensions. The interesting thing is those papers will be written with suggestive examples, which would have things which would make sense from a symbolic level, but that's not, there is no guarantee that the system actually can find those abstractions. Which brings me to the very last slide that I already mentioned this, I believe previously, that symbols, sensory information, this is neurosymbolic. The point is that you could do neurosymbolic for the abstraction reasons, which is basically what is called internal symbolic reasoning, where the system is trying to improve its efficiency by essentially just kind of aggregating states, finding lower dimensions, doing dimensional reduction, etc. And when it does that, it might improve its performance, but it doesn't mean that its abstractions make any sense to anybody else, especially you. Like whenever you have a multi-layer neural network, there is some abstraction. It doesn't make any sense to you. I mean, you can spend your time trying to kind of lobotomize the neural networks. I think lobotomizing AI systems is a dumb way to do it. That's what I'm saying. We should depend on that. Okay. So the other option, so this is a reasonable thing. Lots of people do this, but you can also say, let them do whatever the heck they want. I don't care. As long as they talk to me in the language I understand. You see what I'm saying? And so if you can talk to me in terms of symbols that I understand, and if you can take advice in terms of symbols that I understand, then I'm fine. This is a different argument for neurosymbolic, where you should have a symbolic persona. I don't really care whether you use symbols. If you use symbols that you learned, I'm pretty darn sure that they won't make sense to me. Unless you tell me what symbols to learn, in which case, again, it's not learning. Do you see what I'm saying? What is the chance that some alien, quote unquote, clustering thing will just automatically segment the world exactly the way we segment it? There's like no reason. But as long as it can take our advice and give explanations in the way we want it, we are fine. We don't care what kind of abstraction, whether or not the abstractions it does make sense to us. So this is basically what I care about. This is actually what I was talking in that workshop too, saying if you want to be surrounded by safe AI systems, you should be able to talk to them. Saying looks like my AI system is not doing what I wanted and feeling sad about it makes no sense. So let's design them in such a way that if you have a constraint, the way you can express it, the system knows how to interpret. And if you want the system to say, why did you do this decision? It knows how to give that explanation in language that you understand. Okay, and so that basically comes back to that. And as I said, the last thing that I want to mention is next week we'll talk two different papers. One is a paper which basically starts with plan traces, symbolic plan traces, and learns PDL model from it. So imagine the following inverse problem. Suppose I have a PDL planner, a PDL model, and I gave it a whole bunch of initial goal states. It generated plans. Now I threw this thing out the window. I just took the plan traces. This is what we do in modern AI. We take knowledge, convert it into data so that we can reconstruct it as knowledge, and then becomes learning. Okay, so now I threw this out and I have these plan traces. Can I reconstruct the model? It's a reasonable inverse problem. That's one type of learning domain dynamics. Just domain dynamics, not control knowledge. The other type of learning domain dynamics is the one that I was telling you about, which is basically the people who essentially look at the world at the space-time signal tubes, basically sensory information, and try to learn abstractions in that. That improves the internal speed. And so you say, look, before and after, I have faster performance. But it doesn't necessarily mean that you know anymore what the system is doing. It has a model that it learned from pixels and some sensory information. So you'll read both of these so that you'll get a good sense of both. Thank you.
Godspeed, Raj.